And then I never, so anyway, you don't care. All right, so here we go. The chapter we're starting today is on work, what's called work and energy. So this is always a tough unit to begin, because technically speaking, to have a really good understanding of energy, you need to understand work. But I can't teach you about work until you've learned what energy is. All right? So it's this sort of like circular, you have to understand one thing to understand the other thing. So what I'm going to ask you guys is, so the first two lectures are about different types of energy. All right? Today we're going to focus on kinetic energy, which is energy of motion. Tomorrow we're going to focus on potential energy, which is stored energy. Okay? And you'll have a couple assignments on those two things. The next chunk will be sort of like a kind of an overarching, here's how everything kind of fits together. All right? And then what you'll see is by the end, there's basically two types of problems. Problems where your energy is conserved and problems where your energy is not conserved. But it takes a while for us to sort of build up all the blocks for you to understand that. So today I'm going to be talking a lot about energy, but I'm not going to give you a great definition of sort of what energy is yet, because I can't do that until I've taught you what work is. So I guess my point is I'm going to ask your patience a little bit as we work through the first couple sections of this. You're going to just kind of take some of these terms for what they are and just kind of deal with pointing through the calculations. And after we get a little bit into it, the pieces will start fitting together for you. Does that make a little bit of sense? Okay. Yeah. So, I'm asking for your patience. It's a hazard of this chapter. So, all right. So anyway, so here we go. We're going to start talking about energy today. Specifically, we're going to talk about kinetic energy. My guess is at some point in middle school, you guys learned a little bit about kinetic energy, right? So, what do you guys know about it?
Energy of motion.
Yeah, exactly. It's energy of motion, right? And I think if you look in your notes, it says exactly that, right? All right. So, kinetic energy is the energy of a moving object. All right. So we're going to use the symbol Ke for kinetic energy. The equation to calculate kinetic energy is this. Half of the mass times the velocity squared. All right? And basically, notice that any object that's moving is going to have both mass and velocity, and therefore it'll have kinetic energy, right? If the object is not moving, then your velocity would be 0, which would make your kinetic energy 0, right? Okay, so the kinetic energy of this sitting here is 0 right now, whereas my kinetic energy, because I'm moving around, is not 0. All right? As the equation shows us, the kinetic energy depends on the mass of the object and on the velocities. So you need to make sure you take both of those things into account. And, you know, kind of intuitively, the more mass and the more velocity it has, the more kinetic energy it has. Cool? All right, so let me kind of run through a couple quick examples here. These examples are going to be a little bit not silly, but they're simple. So the point of them is a couple things. One, I want to make sure you guys understand the units. Two, I want to make sure you understand in a little bit more detail the relationship between the mass, the velocity, and the kinetic energy. Okay? So here we go. Let's do our first example here. All right, so here we go. Example, Carl the cat, who has a mass of 3 kilograms, and Dave the dog, who has a mass of 6 kilograms, are going for a walk together.
Aww.
Isn't that nice? Oh, it says that. That's funny. I wasn't even thinking about that when I said that.
That is so false.
All right, they both walk at 4 meters a second. All right, so we're going to find their kinetic energies. So let's get one little column over here for Carl the cat, and over here we'll do one for, what is it, Doug? Dave?
Good job.
Dave the dog? All right, so here we go. So Carl has a mass of 3 kilograms. He's got a velocity of 4 meters a second. We can certainly find the kinetic energy by simply using the equation. It's basically just plug and chug, right? Again, part of the point of this example is I want you to be thinking a little bit about the units. So let's see, we're going to get half. Carl's mass is 3 kilograms. His velocity is 4 meters a second. Don't forget to square it. Please notice, you guys, it's just the velocity here that's getting squared. Okay? So you're going to have 16 times 1.5 gives you 24. All right, and then the units you get are, well, if you just go straight through, you're going to get kilograms times meters squared per second squared. Okay? But that's a bit much to write every time we do energy, right? So another way you could write this is you could write this as 24. It turns out to be the same as Newton meters. All right, because remember, a Newton is a kilogram times a meter per second squared. So when you multiply meters per second squared by meters, you get meters squared per second squared. Cool? Yeah. Even that's a bit much to write. So we're going to replace all of that with a capital letter J, which stands for joules. All right? So when they sort of designed the metric system, they were smart about it. And they said, well, let's make sure that our metric unit of measurement corresponds to our metric measurements of forces and distance and mass and everything. So 1 joule is equal to 1 Newton meter. As long as you keep everything metric, our units will always work out nice and friendly. Just like Carl and Dave. All right, are we good? Do we have questions about how I calculated the 24 joules? Do we have questions about what a joule is? What's up?
The same thing as
Yes, Newton meter, yes. Oh, I'm glad you just said that. We've seen Newton meters somewhere else before, haven't we? Where else did we see Newton meters, you guys remember?
Torque.
Well, we just did torque. All right, torque is also measured in Newton meters, but it turns out they're not the same thing. And the reason for that is mathematical. It has to do with the way that the vectors are multiplied. When you find torque, I don't know if you guys remember, I told you it was a cross product.
Yes.
So torque is a vector. When you find energy, it's what's called a dot product. And so your answer is not a vector. Long story short, these Newton meters here that we use to measure energy are not the same Newton meters that we use to measure torque. Okay, and a better explanation requires more math than I want to go into right now. But good? All right. Any questions about Carl? All right, now Dave over here. Almost the exact same calculation. His mass, though, is 6 kilograms. So when I find his kinetic energy, I've got twice the mass. So what do you think is going to happen to the kinetic energy?
Twice the kinetic energy.
Should be twice the kinetic energy, right? So let's see what happens. Half 4 kilograms. No. Half of 6 kilograms times the velocity. Don't forget to square it. And it does, in fact, give you 48 kilogram meters squared per second squared, or 48 joules. And so what we've just discovered is this relationship. I have just learned that the kinetic energy looks like it is proportional to the mass. Right? Double the mass gave me double the kinetic energy.
Did you drop the
I did not use the fish because the fish is angular acceleration, and I thought that would be confusing. Have you guys seen this notation for proportional?
Nope.
No? Okay. It's the same as, this is what Will was just asking about. You've probably seen this, right?
Oh.
This is proportional to that.
Isn't that like
But I didn't want to use this notation because I didn't want you to think I meant angular acceleration. Okay? So sometimes you'll see this notation means the same thing. It just means it's proportional to. Good? Directly proportional, to be specific. All right, everybody good? Do we have questions? All right, so before we turn the page, let me tell you where we're headed. So take a look at these two numbers. Dave has more kinetic energy than Carl, right? Why? He's bigger, he's got more mass, and they're going at the same velocity, right? So what happens is on the next page, Carl gets a little jealous. He's like, whoa, Dave, dude, what's going on? We're walking at the same speed, but you have more kinetic energy than I do, and that's not fair. So Carl starts running faster. He runs twice as fast, figuring, oh, well, that'll double my kinetic energy, and I'll have just as much kinetic energy as Dave does.
But no.
But no! What does it do? Quadruples it, right? Why?
Square.
Because the velocity is squared in our equation, right? So let's run through that calculation real quick and make sure that it works. So Carl's jealous. He runs twice as fast. So now we've got a mass of 3 kilograms, but a velocity of 8 meters a second. Which, notice, that's the same as 4 meters a second times 2, right? Just for clarification, right? We doubled our velocity. All right, so our kinetic energy ends up being instead of writing 8, I'm going to write 4 times 2. See what happens? So then you get 1/2 times 3 times 4 squared times 2 squared. So you end up getting 24 times 2 squared, or 96 joules.
So those new velocities, 8 pounds. But like it didn't have to tell you that, right? It wouldn't have to tell you that.
It wouldn't have to tell you what.
If he's running twice as fast, you can just assume.
Oh, right, yeah. Correct, yeah. Okay. Everybody understand what I did here, or did I lose you there? Are we good? All right, so would it be true to say that kinetic energy is proportional to velocity?
No.
No, we would have to say kinetic energy is proportional to... Very good. Very good. All right. And does everybody understand sort of the mathematical significance of that? So if my velocity gets multiplied by 10, my kinetic energy gets multiplied by 100. Awesome. All right, cool. All right, and then finally, notice here in green, if neither one is moving, then the kinetic energy for both of them will be 0, right?
Yep.
All right, any questions about kinetic energy? All right, now, one of the things that we will be doing very frequently, guys, as we move forward in the chapter, is there will be problems where you find the kinetic energy and use that to find the velocity. So we got to be able to go backwards, which, easy peasy, right? So check it out. So in this one, it says, how fast would Dave have to go if his mass is 6 kilograms and his kinetic energy is 300 joules? So obviously, you can take these numbers and plug them into this equation and solve for V, right? But we're going to do that so often, I kind of want to just come up with a new equation that allows us to solve for velocity, because we're going to be using it all the time. All right? So if you begin with this, KE equals 1/2 mv squared, and solve for V, well, let's see, I should multiply by 2 to get rid of the 1/2. And now to solve for V, I can divide by m, and then just take a square root, right?
Yep.
So we get V equals 2ke over m squared e. Cool? So, in a few weeks, when we get to the test on this chapter, I will give you this equation here, because it is a definition. I will not give you this equation, because I'm mean. And because you can all do algebra, and we're going to use it so many times you're going to have it memorized anyway, and I won't have to give it to you. All right? There are really not very many equations this chapter. There's like, it's 5 equations or something like that. Okay? All right, so everybody good with what I did here? All right, so we can now find the velocity that they would have to have, right? So it's going to be 2 times 300 joules divided by its mass, 6 kilograms. Don't forget the square root. And you get 10 meters per secundo. Problems? All right, so everything that we just talked about here, kinetic energy depends on the linear velocity of an object. All right, when this tennis ball is moving, it has kinetic energy because it's physically moving, right? Okay. Now, it turns out that, are there any questions on this before we move on? It turns out that an object that is rotating also has kinetic energy. So this tennis ball rotating also has kinetic energy, even though it's not physically moving. Okay? Because the individual molecules are moving, even though the whole ball itself isn't moving. Okay? So, what we're going to do, we're going to kind of run through all this rotational kinetic energy stuff. And at the beginning, it's going to be really like, I think you're going to be intimidated by it. It's going to be like, it's got to deal with all that stuff we had to deal with last chapter. Which is true a little bit, but most of the time, as you'll see, the angular stuff goes away in these problems. Okay? So if you bear with me for a little bit, I'll show you why. All right, so this page is basically the exact same page that we had for kinetic energy. Okay? Notice, rotational kinetic energy, instead of being mass times velocity squared, Remember, mass is inertia, right? So rotational kinetic energy is rotational inertia times rotational velocity squared. Cool? So it's the same equation, right? Just the rotational counterpart for it. Good? All right, and an object that's not moving has no kinetic energy. An object that's not rotating has no rotational kinetic energy. Cool? All right. What's that? Yeah, I was adding emphasis.
Oh.
I did it on purpose. I'll stop now. All right, are we good? Okay. I'm sorry. All right, so let's do an example. Now, I realized last hour running through this, I did not give you enough room to do this example. So if you're somebody who's going to get bent out of shape about that, you might want to pull out a blank sheet of paper and just write like C, and then, you know, whatever, put a number on your page of paper, all right? Okay? So I apologize. I know this sucks if you're trying to keep your notes straight when I didn't give you enough room. All right. So here's the deal. In this example, it says a hoop and a solid disc each have a mass of 3 kilograms and a radius of 0.2 meters. So a hoop and a solid disc each have a mass of 3 kilograms and a radius of 0.2 meters. If they're each rolling at 4 meters a second, then find their RKE and their KE. All right, so look, you guys. If the wheel was simply moving, then it would have kinetic energy, right? If it's just spinning, then it would just have rotational kinetic energy, right? But if it's rolling, it has both, right? Because it's both rotating and moving, right? Follow? All right, so what we're going to do here is we've got these two objects. We're going to calculate the kinetic energy using the kinetic energy equation. We're going to find the rotational kinetic energy using the rotational kinetic energy equation, and then add them together to find sort of their total kinetic energy. Okay? Now, this is going to be tedious. There's going to be a lot of numbers to keep track of. At the end, we're going to realize something. We're going to go through all these calculations, and darn it. At the end, you'll see something. You'll be like, oh, I see something. And it'll give us a shortcut, all right, that will prevent us from having to do all the calculations we're going to do this time. Follow? So let's do it. All right, so first of all, let's do everything for the hoop. Is that about the halfway point? There we go, good enough. Okay, so here we go. What do we know about the hoop? We know that it has a mass of 3 kilograms and a radius of 0.20 meters, and it's rolling at 4.0 meters a second, right? What's wrong?
It's wait. Never mind. I have a question.
All right, is everybody good? All right, so we got to find the RKE and the KE. One of those two things is real easy to find. We can find the KE pretty easily, right? So let's take a second to do that. So the kinetic energy here is going to be 1/2 mv squared. So that's 1/2 of 3 kilograms times 4 meters a second. Don't forget to square it, and you get 24 joules. It's the same thing as Carl the cat, just by weird coincidence. Cool? So there's our kinetic energy. All right. Now, the next thing we need to do is we need to find the rotational kinetic energy. And in order to find the rotational kinetic energy, I need to know I, and I need to know omega. So let's take a moment and do that. So I, does anybody remember by any freakish chance what I for a hoop is?
MR squared.
It is mr squared. So let's see, our mass is 3 kilograms. Our radius is 0.20 meters. Don't forget to square it. Do that and you get 0.12 kilogram meters squared. So there's my I. Sorry. Everybody good? All right, what else do I need to find?
Angular
angular velocity, omega, right? So let's do that. So omega is, well, let's see. I know this stuff. Anybody see an easy way to find the omega?
Divided by
Good, v divided by r, right? Use one of those jumper equations from last chapter, right? So let's see, our velocity is 4 meters a second. Our radius is 0.2 meters. Divide this and you get 20 radians per second. Now we can find the rotational kinetic energy. So let's do that. RKE equals 1/2 I omega squared. All right, so the main reason I'm dragging you guys through all of this is I want you to see how to calculate rotational kinetic energy using I omega. Okay, and it's basically just kind of plug and chug, right? In a minute, I will show you a super secret ninja shortcut. You guys are going to be like, whoa. It'll be amazing. Are you guys ready to be amazed? Because it'll happen in about 5 minutes. 20 radians per second. Don't forget to square it.
Oh, that's plus 1, 2.
Who has a calculatrix?
24.
24 joules, huh? Okay. So there's our RKE. All right, anybody notice anything? What do you got? What are exact same? Oh, you're right. The kinetic energy and the rotational kinetic energy are the exact same. I wonder if that will always be true.
I don't think it is.
Gosh, that would make it super easy, wouldn't it? It's not quite that easy, but it's almost that easy. All right. So, but good. We're making progress. So we just found our KE and our RKE, right? All right. Let's repeat the process now for the disk. All right. So I'm going to go over here. We're going to kind of repeat the same calculations. All right. When do we get out? Oh, 9?
15.
Oh, 15. That's right. Monday. Cool. All right. So here's what we know about the disk. We know it has a mass of 3 kilograms. We know it has a radius of 0.20 meters. We know it has a velocity of 4.0 meters a second. And so its kinetic energy is going to still be 24 joules, right? Does everybody see why? Same mass, same velocity. You're going to get the same kinetic energy, right? Everybody happy?
Yep.
Problems? Some people are still writing. I will give them a moment to get caught up. Give me a moment to drink some water.
So, Mr. Hacker, is this like going to be like the base equation that like it's going to be to this or not?
What do you mean?
Like where the kinetic energy and rotation are going to be? If the equation is this or no?
You're warm. You're right to be looking at those equations. You might even be saying the right answer, but just saying it and not
Like go in
fully explained. Yeah. All right. Is everybody good with what I've got so far? All right. So now we need to find the rotational kinetic energy for our disk. So to find the rotational kinetic energy, I need to know I. So what is I for a disk? Instead of being mr squared, it's 1/2 mr squared. So that's 1/2 3 kilograms. Wow. Times 0.2 meters. Don't forget to square it. And you get 0.06 kilogram meters squared. Okay. We can find, everybody okay? Our omega is going to be the same thing, isn't it? It's still going to be 20 radians per second, right? Oh? Am I right? Is that,
You're right.
why am I uneasy about something? Velocity, same velocity. Yeah, I guess so. Okay. All right, so here we go. Let's find our RKE. So RKE is 1/2 I times omega squared. So that's 1/2 0.06 kilogram meters squared times, oh right, 20 radians per second. Don't forget to square it. And you've got 12 joules. Now what do you notice? It's half as big.
Oh, it's all right.
Where did the 1/2 come from? From our I. Yes.
I'll get it.
Yes. All
I
right.
don't like it.
Okay. So in this one, notice this I here. I could write this I as 1 times mr squared, right? And notice my rotational kinetic energy is my kinetic energy times 1, right? Over here, my I is 1/2 times mr squared. And my rotational kinetic energy came out to be my kinetic energy times 1/2. All right? Here's kind of the deal with it. All right? So note, if an object is rolling, now when I say rolling, I mean it has to be rolling, not spinning, not sliding. It's got to be literally rolling. So I can't emphasize this word enough. And I equals, all right, well, we need to find a way to write a general expression for I. So I is always something times mr squared, right? If you look on those sheets, they all have m times, you know, they might use a letter other than r, but whatever, it's m times something radius squared, right? So, but we need a fraction here, right? Sometimes it's 1/2, sometimes it's 2/5, whatever. All right, I'm going to use what they use in the AP book, which is the Greek letter beta. So, for a disk, beta is 1/2. For a solid sphere, beta is 2/5. For a hollow sphere, it's 2/3. So let me pause for a minute. Does everybody know what I'm talking about here with this beta thing?
Mm-hmm.
So beta is just some fraction that you get off of that little sheet, right? Pretty good? Then, check it out. Rotational kinetic energy is 1/2 I omega squared, right? But let's do a quick substitution. This is 1/2 of, well, I is this. It's some fraction, which we're going to call beta, times mr squared. So that's I. And then what's omega, you guys? How did I find my omega on...
If I remember.
Oh, omega is just v over r, isn't it? Ugh.
Oh, what?
So omega is v over r. So I'm going to replace omega with v over r, and I'm going to remember to square it. The equation says to square it. And what do you notice?
Wait, you can cancel the R squared.
Holy cats, you can cancel the r squared.
Okay.
Oh, that was good. I like that. Holy cow, that was good. So you get 1/2 beta times mv squared. Hello, how are you? What's the message?
Yeah, I see.
Got it. All right, and then what's 1/2 mv squared, you guys?
1/2. No, that's. Wait, that's KE.
What? 1/2 mv squared, that's KE. So this is,
I know.
so this is beta times 1/2 mv squared, which to be honest, very often we'll leave it this way. But you could also write it as beta times KE. Well, those are both scalars, actually, so I know you were doing. All right, does that make sense, you guys? So if something is rolling, once you've got the kinetic energy, then finding the rotational kinetic energy is easy, right? You just multiply by whatever that fraction is in the I equation. Cool? Are there questions about this beta? Are there questions about any of this mess? Okay. When are we allowed to use this trick? If the object is rolling, not just rotating. Here's why. Look. Does it, right? What's the kinetic energy? 0. But it has rotational kinetic energy, right? So it has to be rolling for this to work. Because it relies on this jumper, v over r, and that's only true if it's rolling. So that the velocity... All right. Okay, so we got... Woo. So we got 3 quick examples to do here. It's worded awkwardly, and I wish I had caught this before I printed them up for you guys, but I didn't. So here's the deal. So I'm going to give you a basketball under 3 different circumstances. All right? And I want you to tell me how fast it needs to be moving or turning so that its total kinetic energy is equal to 6 joules. All right? So in the first one, the basketball's just spinning, and we want the RKE to be 6 joules. In the second one, the basketball's just moving, but not turning, and I want to know how fast it needs to be moving. And then in the last one, it's going to be rolling. So in this last example, we can use that little trick that I just showed you. Follow? But it will only apply in that last example. All right? Okay, so here we go. So the first, it's really worded badly, like I say. So for this first one, we got to be finding angular velocity. It says at what velocity would let's write down our numbers. The mass is 0.60 kilograms. It's got a diameter. Why did I do that? So what should I do with the diameter? Cut it in half to get the radius. So the question is, what velocity would it have to spin at to have 6 joules of energy? Well, if it's spinning, what kind of energy will it have?
RKE.
RKE, right? Sorry, I keep...
Look, I tried to cover it.
I know, right? You can see it on my hand. All right. Okay, so the idea is because it's spinning, this 6 joules of energy is RKE. Follow? Right, and so the question is, what's the velocity? In this case, we're going to be looking for angular velocity, right? Good? All right, so here we go. So the equation that relates these is RKE equals 1/2 I omega squared. So to find my omega, I need to know I, right? So it's a basketball. So what is I for a basketball? It's a sphere. There are 2 spheres on the sheet. One of them's 2/3, one of them's 2/5. Some are squared. Yeah, it's hollow, so it's 2/3, right? So 2/3 of the mass, which is 0.6 kilograms, times our radius, which is 0.12 meters. Don't square it. And it gives you 0.00576 kilogram meters squared. Cool. All right, so now we ought to be able to rearrange that RKE equation to find our omega. Omega is 2 RKE over I square root E. That equation should look vaguely familiar, right? It's the same as the V equals 2KE over M equation. All right, plug your numbers in. You get 2 times 6 joules over 0.00576 kilograms meters squared. Don't take the square root. And if you do that, you get a number 45.6 radians per second. All right, that was honestly, of the 3 parts, that was, I think, the hardest one. Or maybe not hardest, most tedious. Sorry. Problems with how I did that, you guys? Okay, cool. So now B. What if instead of spinning, what if the ball was just sliding through space? Well, then we'd have the same mass. The ball would still have the same radius, although it wouldn't affect the problem. But what kind of energy would it have now? Instead of rotational kinetic energy, it would be just regular kinetic energy, so that would be 6 joules. And the question now is not what's the angular velocity, but what's the regular velocity? Follow? Any problems? Am I going too quick? Okie dokie, so here we go. So our V is 2KE divided by M. Don't forget your square root. And so you get the square root of 20, which gives you 4.47 meters a second. That one was not too bad. Everybody good? We have just enough time to do that last one. And then I will tell you about homework stuffs.
Oh, wait, no.
Yes-ish. It's half an ish. Okay, can I go on? Are we good? All right, last-ish. I know I said ish again. All right, so now what if it's rolling? Well, the ball still has the same mass, still has the same radius, which ends up not mattering. We're trying to find the velocity that it would have to roll at in order for the kinetic energy to be 6 joules. But what kind of kinetic energy are we talking about now? Both, right? It's rolling, so it's got both KE and RKE. So we need KE plus RKE to be 6 joules.
Whoa. That's really weird.
Plus RKE?
That's really weird.
Like add them together?
Like add them together and they're 6 joules. Okay, the idea is the thing is rolling, so it's got 2 types of kinetic energy.
You think you're funny.
Do you guys understand why it's both? We're good, Matt? Are you good? Yeah. Okay. All right, so look, this ends up not being that bad because look. So let's see, kinetic energy. Well, that's 1/2 mv squared plus, remember I showed you the super secret ninja shortcut if it's rolling? So my rotational kinetic energy should be what? Same as the kinetic energy, except
The fraction.
the fraction thing. So what's my fraction? Why is it 2/3?
Because that was the I thing.
Because that was the thing in our I,
With the thing.
the beta, up here. Here's my beta. Beta, right, is 2/3. Follow? All right, and so this whole mass has to equal 6 joules. I'm using red now. Deal with it. All right, so what do we get? You get 1/2. The mass was 0.6 v squared plus 2/3 of 1/2 times 0.6 v squared equals 6 joules. So this gives you 0.3 v squared plus, let's see, this is 1/3 of 0.6 is 0.2 v squared equals 6 joules. So you get 0.5 v squared equals 6 joules. V squared equals 12 joules. Oh, wait a minute, my units got funny. What did I do? Oh, because I divided by 0.5, so it's not joules anymore. So, fail.
So that's my contact starting to know where these ducks.
That 0.5 here has units on it that I lost when I did my algebra here. What units should my velocity turn out to be in, though, you guys? Meters a second, because everything we did was metric, right? So the square root of 12 is, I think, 3.46. There's your answer. All right, does that make sense? Okay, that is as hard as they get at this point. And honestly, I don't know that they get too much harder than that, except just so there will be more steps to get to them. All right, due on Wednesday. Worksheet 8.1a. Due on Thursday is worksheet 8.1b. Okay? Tomorrow, more notes.
Right starts already? Oh my god. This year's going for so
Thank you for reminding me.